Welcome to this course on good pipetting techniques. We will review a range of pipetting techniques and show you the positive effects that improving technique can have on reducing errors and ensuring data quality. To start with, we would like to give you an example how small pipette errors can accumulate and lead to failed experiments. This slide shows a typical experiment that requires a serial dilution. In this case, the experiment requires inoculating test mice with a virus at the LD50, the dose level of virus that kills 50% of the mice. Prior to this, the viral stock must be quantified using a serial dilution. The critical issue in preparing the serial dilution is to make sure that the process is accurate so that mice are neither over nor under-infected, since both cases give incorrect results. As shown here, under-pipetting by 5% results in an apparent titer that is only 74% of the correct titer, which in turn leads to over-inoculation and death of all the mice. Conversely, over-pipetting by 5% leads to overestimating the titer by 34%, which leads to under-inoculating the mice, resulting in all live mice. In both cases, the experiment has failed. This clearly shows you how important it is to know about correct pipetting technique in order to avoid pipetting errors and failure of experiments. Before we begin our review of specific pipetting techniques, I want to define pipette accuracy, as well as another important term, precision. Accuracy is the ability of a pipette to provide a dispense close to the volume, as indicated by the volume setting. Typical accuracy specifications for air displacement pipettes are approximately 1% for pipettes with nominal volume settings greater than 35%. For pipette volume settings at 10% or below, the specifications can be as much as 3 times less accurate. Precision is the ability of the pipette to provide reproducibly similar dispenses. A typical precision specification for air displacement pipettes is about 1/3 to 1/4 of the accuracy specification. Precision is often referred to as repeatability or sample reproducibility, and also as standard deviation. The 3 images of targets demonstrate the concepts of accuracy and precision. Imagine that each shot on target is like an attempt at pipetting, and the bullseye is the target volume. The image on the left, neither accurate nor precise, means the results are scattered haphazardly. The image in the middle, precise but not accurate, means all the results are close to each other, but shifted together away from the goal. The image on the right, accurate and precise, of course means all the results are clustered around the bullseye. Now that we've discussed terms such as accuracy and precision, let's talk about the basics of proper pipetting technique. We'll review some recommended techniques to help you improve your pipetting results and achieve the best possible accuracy and precision in your work. Specifically, we will review some of the basics of pipette technique sequentially, in the order of how you would use the pipette. However, given that this is an overview presentation, I will be focusing on just the most important techniques. We will cover selecting optimized volume ranges, recommended tip immersion angle and depth, review the effects of sample aspiration rate on pipetting technique and results, discuss the importance of consistency in pipetting technique, Review the importance of using appropriate pipetting technology for difficult liquids. Overall, errors from any of these poor techniques can range from 0.1% to 5% or more. Here is an example of some pipette manufacturing specifications. These accuracy and precision numbers are what the manufacturer guarantees their pipettes can perform to. However, regardless of manufacturer, getting the pipette to actually perform to these specifications requires excellent technique, especially at the low volume ranges. On this slide, we will have a closer look at the pipetting cycle. The pipetting cycle for air displacement pipettes involves 5 steps, as illustrated in this chart. This is the typical way most people pipette, called forward pipetting. We will cover reverse pipetting in a bit. The size of each segment corresponds to a typical amount of energy or force required for each step. I'm sure most of you are familiar with this cycle, but I would like to review it briefly. Place the correct tip onto the shaft or liquid end of the pipette. Remember, with universal fit systems, you will want to ensure that the tip is secure to prevent leakage. With Rainin's LTS system, this extra caution is unnecessary because all tips seat and secure the same way. Step 1 is to depress the plunger from its resting or home position by pushing down on the button at the top of the pipette until it reaches its first mechanical stop. Then hold. Step 2. The pipette tip is then inserted into the liquid sample, and the sample is aspirated by releasing the plunger button slowly, allowing the plunger to move upward to its home position. Step 3 is dispensing your sample by again depressing the plunger button smoothly to the first mechanical stop and pausing momentarily. Step 4 is pushing the plunger past the first stop until the second mechanical stop is found. This step allows any remaining sample to be fully expelled from the tip. A touch-off will be required, which we will cover shortly. After this, the plunger is returned to its resting position. Step 5 is tip ejection. The normal operating range for most pipettes is 10 to 100% of nominal volume. Although this is considered to be the operating range of the pipette, the performance specifications will change as the volume setting decreases. For example, the accuracy specifications for a 2 microliter pipette are plus or minus 1.5 to 2.7% from 50 to 100% of nominal. But if you were to dial the volume setting to 0.2 microliter, which corresponds to 10% of nominal, the inaccuracy specification would be more than 4.5 times greater, actually 12%. Using this pipette at these lower volumes requires you to be aware of inaccuracies and adjust your techniques accordingly. So, a consequence of this is that it is better to avoid pipetting at 10% volume when you can. For example, if you need to pipette 2 microliter, it is better to use a 2 microliter or 10 microliter pipette than a 20 microliter pipette. When setting the pipette micrometer, it is important that you always approach the desired volume in the same direction each time. The recommended technique is to dial down to the desired volume setting, rotating the volume selector knob clockwise. When decreasing the volume setting from a higher to a lower volume, simply dial down to the desired volume setting, being careful not to overshoot the required position. When increasing the volume setting from a lower volume to a higher volume, rotate the volume selector wheel or knob approximately 1/3 of a turn above the desired setting, and then slowly turn back clockwise to decrease the volume until you reach the desired setting. The dial-down technique reduces the effects of mechanical backlash or slippage of the micrometer gears and ensures better accuracy. This slide illustrates on how to correctly aspirate the sample. Using an incorrect immersion angle is one of the most common incorrect pipetting techniques. I'm sure all of us have watched someone hold, or done it ourselves, a pipette at a 45-degree angle when aspirating a liquid sample. In fact, Rainin recommends keeping the immersion angle as close to the vertical position as possible, or at no greater than a 20-degree angle from the vertical. Aspirating a sample at an angle of greater than 20 degrees has been shown to affect sample accuracy by up to 0.5% for normal models, and by up to 2.5% in micro-volume pipettes. Not only the immersion angle, but also the immersion depth of your pipette tip can also affect your results. If the tip is immersed too deeply, liquid will rise into the tip because of the effects of air pressure. In this case, you could aspirate more sample volume than you desire. If the tip is not immersed deeply enough, air could be aspirated into the tip, and your pipette will not accurately aspirate the selected volume. It is also possible that insufficient tip immersion depth could result in sample splash-up effects. We will discuss the problems associated with sample splash-up later. Based on our studies, the impact on larger volume pipettes is far less significant than on micro-volume pipettes. For accurate and precise results, Rainin suggests maintaining the recommended immersion depths shown on this slide. As a general guideline, the pipette tip should just break the surface of the liquid sample. Maintaining consistency in your pipetting technique is important to achieve high accuracy. Rainin recommends that you use a consistent pipetting rhythm from sample to sample. For example, when using a macro volume pipette, 1 milliliter or greater, it is important to pause after sample pickup and allow the sample to fully aspirate before removing the tip from the liquid. A minimum of 1 second of tip immersion time is recommended. Releasing the pipette plunger button too rapidly can cause several technique-related problems, such as fountaining, sample splash, or bubbles. When using macro-volume pipettes greater than 1,000 microliter volume, it is important to maintain sufficient tip immersion time after aspirating liquid samples. Allow a minimum 1 second pause after aspirating before you remove the tip from the liquid. This provides sufficient time for the liquid and air interface to reach equilibrium in the tip. After the 1 second pause, completely withdraw the tip smoothly and slowly from the liquid sample. Sometimes you can see an air gap at the bottom of the tip orifice or opening with macro volume pipettes. This air gap could be caused by several factors. Reason 1, the tip may have been inserted into the liquid from an angle more than 20 degrees to the vertical. Reason 2, the user failed to pause for at least 1 second after aspirating before the tip is removed from the liquid. Each of these factors will affect the accuracy of the sample delivered. Another factor is, even after you have done everything properly, the pipette is being moved about after aspiration and an air gap appears. This is just settling of the air interface, which acts like a spring and will not affect the accuracy of the sample. At the end of the pipetting process, as the sample is being expelled, there are several options to ensure that any remaining liquid is expelled from the tip. You can combine these options. They are not mutually exclusive. Option 1 is to dispense into the liquid. However, this can cause liquid to cling to the outside of the tip, or the accidental aspiration of liquid back up into the tip. Option 2 is to dispense above the liquid. This, however, especially for micro volumes, can cause aerosols which can land on the sides of the tip. Both of these options can adversely affect accuracy and precision. Ideally, during blowout, slide the tip along the side of the container wall while pulling up to ensure that all liquid has been expelled. This is called touch-off. When dispensing viscous liquids, pause before blowout to ensure that everything has been expelled. Dispensing directly into the liquid is the most common technique. If dispensing directly into the liquid, you might want to consider touching off along the side wall to ensure that all liquid remains in the tube. Something else that is important and increases the accuracy of your results is pre-rinsing the tip. Pre-rinsing 2 or 3 times forms a liquid film on the inside of the tip that can increase accuracy by up to 0.2%. Pre-rinsing helps neutralize capillary effects in micro-volume pipettes, and for large volume tips, equalizes the air temperature inside the tip with the temperature of the sample. Maintaining consistency in your pipetting technique is important to achieve high accuracy. Rainin recommends that you use a consistent pipetting rhythm from sample to sample. For example, when using a macro volume pipette, 1 milliliter or greater, it is important to pause after sample pickup and allow the sample to fully aspirate before removing the tip from the liquid. A minimum of 1 second of tip immersion time is recommended. Make sure you apply consistent pressure on the plunger at the first stop point or hold position. Also, pay attention to a consistent speed and smoothness when pressing and releasing the plunger. With an electronic pipette, you can achieve consistent sample pickup and dispensing, which will eliminate most user-to-user technique variability and improve accuracy and repeatability. Another source of error many people are not aware of are hand-warming effects. During regular use, heat is transferred from the user's hand to the body of the pipette. Prolonged handling of the pipette, such as during micro well plate work, can result in a noticeable deviation in pipette performance. Prolonged handling of a pipette can cause a change in the delivered volume, over time, of as much as 0.5%. This is primarily due to the expansion of the air column inside the pipette from hand warming. Pipette shafts should not be handled before and during pipetting activities, since shaft hand warming effects are more pronounced. The discussion so far about techniques is mainly relevant for air displacement pipettes. Positive displacement pipettes offer some unique advantages, but also have some drawbacks. Most aqueous samples can be transferred accurately with air displacement pipettes, while many problem liquids can be pipetted more accurately with a positive displacement pipette. Let's take a moment to define the differences between the two major types of pipettes. Both methods use the area of the piston or capillary and the length of the piston stroke to define the volume of liquid dispensed. Both technologies rely on the creation of a vacuum as the piston draws upwards. The difference is in the amount of air in the tip. As the piston moves up inside of the air displacement pipette, it creates a partial vacuum, which draws the liquid into the pipette tip. Air is compressible or elastic, and the elasticity limits the amount of force available to pull liquid into the tip. But the air gap also protects the piston from sample contact and allows for an inexpensive disposable tip. Pipettes, such as Rainin's Pipette Light XLS, are examples of air displacement pipettes. In the positive displacement pipette, the end of the disposable piston comes in direct contact with the liquid, and as it is displaced inside the capillary or tip, the liquid sample replaces the void space beneath the piston. Since there is almost no air cushion at all, the vacuum is much stronger, thus providing much greater force, which allows denser and more viscous liquids to be pipetted accurately. The lack of an air gap also makes pipetting volatiles easier, since they cannot evaporate in the tip. However, typically the entire capillary and piston system must be discarded after use, since the piston has contacted the liquid. In summary, the next two slides provide examples of the benefits and disadvantages of the two basic pipette types. There are many advantages of air displacement pipettes. They are very accurate with aqueous solutions at standard lab temperature. They are available in manual or electronic format. If applied correctly, a good pipetting technique can clearly minimize errors. Disposable tips are convenient and less expensive. They require lower ergonomic force. Negative aspects are, they require more training to achieve accurate results, particularly at low volumes. The pipette can be damaged or contaminated if the sample contacts the piston. Inaccuracies can occur if sample of lab temperature differ. The viscosity of the sample is different from water, the sample is too volatile, or the humidity too low and vapor pressure too high. This slide summarizes the benefits and disadvantages of the positive displacement pipette. Advantages of the positive displacement pipettes are: they are accurate with different types of liquids, even if the liquid is volatile or very dense and viscous. They are available as manual and electronic repeater pipettes. Less training is required to achieve accuracy and precision. The pipette is protected from contamination and damage by a disposable capillary system. Negative aspects are: the disposable capillary and piston have a higher cost than disposable tips for air displacement. Higher ergonomic forces are required for pipetting. There is no multi-channel option. This chart shows our recommendations for pipette type in ambient and non-ambient temperatures for aqueous samples. As a general rule, when pipetting aqueous solutions, Rainin recommends using an air displacement pipette. Whether manual or electronic, air displacement pipettes provide the best performance at a reasonable cost when you consider disposable tip usage for air displacement pipettes versus capillary and piston usage for positive displacement models. If the aqueous solutions are at temperatures other than ambient or laboratory room temperature, then Rainin recommends that you not pre-rinse pipette tips before you aspirate samples, and that you consider equilibrating the pipette to the approximate temperature of the sample solution. For example, this could involve keeping the pipette for at least 1 hour in the same cold room where the liquid sample is stored. Alternatively, when pipetting aqueous solutions at temperatures other than ambient, A positive displacement pipette could be used to avoid the potential for introducing errors of inaccuracy and imprecision into your work. Here is a chart to show the recommendations of pipette type in viscous and volatile solutions. For pipetting viscous solutions, such as glycerol, an air displacement may be used in the reverse mode. Generally, using a positive displacement pipette is a better choice for pipetting highly viscous or dense solutions. Samples that have a high vapor pressure or are very volatile will affect pipette performance dramatically and can potentially damage the pipette's internal parts. If accuracy and precision are required in pipetting these non-uniform samples, use a positive displacement pipette, and the pipette is not in danger of damage. We mentioned in the previous slides reverse pipetting, but what exactly is reverse pipetting? Reverse pipetting aspirates more liquid than required, meaning more than set on the micrometer, because it begins by depressing the plunger all the way down through blowout. Then, the correct amount of liquid is dispensed by only dispensing to the first stop, not through blowout. The residual liquid is removed by blowout, either into the trash or back into the original sample container. Studies have shown that this technique can be more accurate for some kinds of liquids, especially dense and viscous. However, it is very technique dependent. Every researcher should determine empirically whether reverse pipetting provides better results for their particular liquid. This slide gives you an overview of the various pipetting errors that can occur and classifies them into small, medium, and large. We talk about small errors when they are smaller than 1% and when only very sensitive applications will be affected. We classify them as medium errors if the error lies between 1 to 5%, and large errors if they lie between 5 to 25%, and therefore could affect all applications. Small errors are affected by micrometer setting, if volume range optimized, tip immersion angle, pre-rinsing, hand warming. Medium errors are affected by optimizing volume range, tip immersion depth, aspiration rate, inconsistency, and the dispensing technique. Large errors are affected by tip immersion depth or angle, ultramicro, aspiration rate, splash up, using air displacement pipette with difficult liquids, viscous, volatile, hot, cold. Keep in mind that errors can be cumulative, so consider this as you decide which techniques to use. The most important consideration should be that good pipetting means good technique equals to minimal errors and results in good data. To recap, today we reviewed a range of pipetting techniques and showed you the positive effects that improving technique can have on reducing errors and ensuring data quality. Today's course was presented as part of Good Pipetting Practice, also called GPP. GPP is a guideline to reducing the risks in the workflow process that involves liquid handling and maximizing the potential to produce accurate, reproducible data. Good Pipetting Practice covers a number of individual components that can be considered individually, but when taken as a whole will lead to improved data generation. Today, we just talked about good pipetting technique, but there is a lot more to pipetting than just that, which we would also be glad to tell you about. If you are interested in our program, visit www.mt.com/GPP for more information. Thank you for your attention.